Welcome everyone to this intermediate experiments in electronic circuits. Today we're going to explore operational amplifiers with a focus on resistors, specifically the complications that arise from tolerance, availability, and discrete values. We'll start with a review of the inverting and non-inverting op-amp configurations. We'll look at gain as a function of tolerance. We'll explore the E series of discrete value resistors, and then I'll present some tools that allow you to quickly find the right resistor combination based on the desired gain. As a starting point, consider the inverting and the non-inverting amplifier. The gain for the inverting is negative RF over Rin, where this is RF and this one here is Rin, where the negative sign indicates that it's inverting, which is to say it has a 180-degree phase shift. As for the non-inverting, the gain is equal to 1 plus R, in this case 2, over R1. Now, suppose we want to set the gain to 7 for each of the op-amps. There are many different ways we can do that, especially when we consider that no resistor values have been selected at this point. To get started, I'm going to assume that R3 is 10K and R1 is 10K. For the inverting, that would mean 7 is equal to negative RF, that's the one we need to calculate, over 10, and it follows that RF is simply 70K. Now, for the non-inverting, 7 is equal to 1 plus R2 over 10K. Solving for that, R2 is going to equal 60K. Another way of thinking about that is the ratio for the inverting is equal to 7 to 1, whereas the ratio for the non-inverting is 6 to 1. Later on in this video, we'll come back to this ratio and we'll use that to select the desired resistors. This is a good time to talk about resistor tolerance. Let's consider both the 10K ohm resistor and the 70K ohm resistor from our previous example. If we assumed 5% tolerance, we would say that it's a 10K ohm resistor plus and minus 5%, and a 70K resistor plus or minus 5%, which means that this resistor can take on values from 10K multiplied by 1.05 and 10K multiplied by 0.95. Whereas on the other side, we get 70K multiplied by 0.95 is less than R is less than 70K multiplied by 1.05. Solving for the values, that means that our input resistor can go from 9.5 up to 10.5. Whereas our feedback resistor can range from 66.5 all the way up to 73.5. This is normal. This is the range of values you would expect if you purchased a 5% resistor. Now here's why it matters. You remember that gain is equal to negative RF over Rin. If we were to take that to the extremes, we would say that gain min is equal to 66.5 divided by 10.5, which is about 6.3, whereas gain max is equal to 73.5 over 9.5, which is about 7.7. That should give you something to think about. So you may have expected a gain of 7, but when you went to purchase your resistors for any given device that you manufacture, you can expect a gain somewhere between 6.3 and 7.7. Maybe that's acceptable, maybe it's not. If it's not acceptable, you're going to need to spend more money. And instead of using 5% tolerance resistors, maybe the answer is that you use 1% tolerance. I'll leave it to you to do the calculations, but you would see that this number here and this number here would be much closer together and closer to 7. Now that we have a better understanding of resistor tolerance and its effect on the gain of an op-amp, we can look at selecting a particular resistor. Before we do that, it's useful to explore what's known as the E series of resistors, which can be found on this Wikipedia page. The information we need is about halfway down the page. Here you can see the different E series. The E series we've mostly been dealing with is this E24 series. Note that it is typically talking about 5% tolerance. And the number 24 is derived because if you look at this, there are 24 discrete values per decade, which means you could buy a 1 ohm resistor, a 10 ohm resistor, a 100 ohm, a 1,000 ohm, 10,000, so on and so forth, just as easy as you could buy a 3.3, a 33, 330, 3.3K, 33K, and so on. Again, 24 values per decade. Based on our gain calculations, it may be useful to jump up to this E96, which is generally considered the 1% tolerance. There are now 96 discrete values of resistors. We could go even higher, for example, the 192, which is the 0.5%. There are 192 values. At this point, we're going to take a closer look at the E24 series. At first glance, this table looks rather confusing. However, it's just a ratio of resistors. For example, across the top are those 24 values, and down the side are the 24 values. Each cell is the ratio of the two resistors. For example, 3.0 to 3.0, you can see the ratio is 1. 3.0 to 1.5, the ratio is 0.5. In order to use this table, all we need to do is know what the ratio of resistors are for a particular gain, and then we can select the best pair. In our earlier example, the inverting amplifier required a ratio of 7. And if we look at this chart, we can find 7 here and here. By the way, disregard any factors of 10 because we can easily find the desired resistors because there are, in this case, 24 values per decade. Suppose we let our feedback resistor be 330K and our input resistor be 47K. We would have a gain of 7.02, which isn't too far off from our desired. Let's try the other pair. Here, let the feedback resistor be 390K and divide that by 56K. We end up with 6.94. Given the two choices, it looks like 7.02 is a bit closer. By the way, sometimes it helps to do this the other way. Rather than saying 0.7, take the inverse of that and that's 1.43. And see if you can find that in the table. There's one here, which suggests a pairing of 3 and 4.3. So if we let our feedback resistor be 300K and our input resistor be 4.3, that gives us a value or gain of 6.97. So far, it's looking like our first choice was the best. Let's see if we have any better luck with our non-inverting amplifier. As you recall, it had a ratio of 6 to 1. So let's see if we can find 0.6 in here. This looks like a very good fit. If we let our feedback resistor be 120K and the other resistor be 20, we end up with a gain of 6.0. So that one actually worked out better given this chart. I'd argue this isn't the most pleasant thing to use, so it might be better if we developed a computer program to do it for us. This is a short little program I wrote in the language of C. I'm not going to show it to you because I think it's a good exercise for you to develop this yourself. That, and maybe someday when I'm teaching, I want to use it as an exercise. However, I can show you what the results are. So let's go ahead and set the ratio to 1 to 7. And you can see in here that I have an array of the E24 values, array of the E96, and array of the E192. So when I hit run, it's going to figure out what the best fit for those resistors are. So we scroll up to the E24 series. It's converging to this number here, which is 1 divided by 7. And it suggests that a 1.3 ohm resistor and a 9.1 would be appropriate for us, which makes me think I missed something on our previous chart. Sure enough, there it is. That 1.3 and 9.1 would have been a much better choice. Let RF be 91K and let the input resistor be 13K. As I said, this chart is a bit inconvenient and it's very easy to miss things. But that's why we make computer programs, to make life much easier for ourselves. So for the E24 series, the best fit would be this 1.3 and 9.1 ratio. If we move to the E96 series, it looks like we found a good match in 9.31 and 1.33. And if we go to the E196 series, we can probably find some real good fits as well. There's an obvious match there with 77.7K as the feedback resistor and 11.1K as the input resistor. Now we can go to a site like Digikey and see what we can find. We'll look at the through-hole resistors. Let's set the tolerance first. We'll go 1% and look for normally stocked items. Let's see if we can find that 77.7 K ohm. It's not available, so let's instead try that 93.1. That one is available in quarter watt, so that's nice. Let's go back and see if the pair of 13.3 is also available. It is, and again as a quarter watt. So there you have it. Given our desire for a inverting amplifier with a gain of 7 using 1% resistors, it looks like a 93.1K and a 13.3K are our best options. I would argue that that solution is in no way intuitive, and it took a fair amount of work to get there. We first had to calculate the ratios, then we had to walk through the E series that interested us, and then we had to go to our distributor and see which resistors were indeed available. I do hope you found this video useful. Please leave any comments, questions, or concerns in the space below.